So I'm going to say a little bit about hemicelluloses now. Hemicelluloses, which I've talked about in other talks, and I've said that they're made up of different sugars and they've got branching and all this kind of stuff. But I'm going to go in a little bit more detail now, and I'm going to look at one specific example to illustrate the principles behind some of the properties of hemicelluloses. And I'm going to look at a hemicellulose called a Glucomannan. And a Glucomannan is made up of glucose units and mannose units. So, as I said before, the position of the hydroxyl groups at the chiral centres in that sugar chain determines the name of the sugar, apart from the fact that the mirror image is either an L form or a D form. Other than that, you may have hydroxyls in different positions, in which case the sugar is given a different name. Now, if we were to look at a mannose sugar, which is also a hexose sugar, we would find this arrangement of hydroxyl groups. It's a bit difficult to draw now. I'll do it in a different colour so that I can illustrate the point. That hydroxyl group is an axial. This is a D form of mannose, and it's a beta D form because analogy with the glucose structure. So we have a structure that is very similar, particularly the way those hydroxyl groups are arranged. But we have this hydroxyl in a different position. So what are the consequences of that? The first thing we do is we can join these molecules together. The glucose and the mannose all join together to form a backbone that is linear. So that linear backbone is quite capable of bonding to the surface of the microfibril because of its shape. And on that linear backbone, we have hydroxyl groups. And those hydroxyl groups are able to match with the hydroxyl groups on the cellulose backbone, the surface of the microfibril. So these ones here are able to hydrogen bond. But we also have hydroxyls that are not in the same position as they are on the cellulose. So these ones are not able to hydrogen bond with their brethren on the cellulose chain. So that has a consequence, and the consequence is that the bond is weaker. So the bond between a Glucomannan backbone and cellulose surface, the hydroxyl-rich surface on the microfibril, is not as strong as the bond between the cellulose chains, the adjacent cellulose chains inside the molecule. So what does that mean? It means nature's being very clever, because I was talking about cracks and interfaces in another talk, and I was talking about the fact that we need a weak interface in order for the crack to be diverted when it meets the fibre. Otherwise the crack will go right through. If we have perfect bonding between the matrix and the fibre, a crack will pass right through and not even know that reinforcement is there. So the toughness of composites comes about by crack diversion, fibre pull out, crack stopping. Those are the three main mechanisms. And that's what this is all about. This is about controlling the strength of that interface. Because the hydrogen bonding isn't as strong as it is inside the microfibril, it is possible for water molecules to get in there and disrupt that to some extent. The extent to which it can be disrupted is very dependent upon how many of these are formed. So sometimes these can be a lot stronger in some situations than others. So that different sugar has consequences because of the position of the hydroxyl. So this is just an example of Glucomannan. There are many, many examples of different hemicelluloses in wood. But they all have this common theme that there is going to be a linear backbone at some point. It may not be all the way through the molecule, it may be chunks of it. But those chunks can come up closely to the surface of the microfibril, but they will not be bonding with that microfibril as strongly as the cellulose chains. The other thing that nature does is it takes some of these hydroxyls in the hemicellulose and it performs a reaction on them using an enzyme to give acetyl groups. And those acetyl groups, I'll stand here so you can see it, these acetyl groups also disrupt the hydrogen bonding. They also change the polarity of the molecule. The molecule, if you start cetylating something, it doesn't have so many hydroxyl groups, so it's not as compatible with water. Lignin, which I'll talk about later, is much more towards the hydrophobic end of the spectrum between hydrophilic and hydrophobic. It's not as water-loving as some of the other molecules, as the carbohydrates, because it has less hydroxyl groups. So by acetylating, we can make the hemicelluloses more compatible with the lignin matrix. So we want the hemicelluloses to act as interfacial coupling agents. We want them to be, well, we don't want them, that's their function. They have to have some compatibility with the reinforcement and some compatibility with the matrix. The other thing you'll find on hemicelluloses is carboxylic groups. Carboxylic groups. These can chemically bond to the lignin. I'll talk about that later when I talk about the lignin carbohydrate complex. We also find aldehydes on there. I'm not too sure what they do, to be quite honest with you. And we also get branching. That's another thing that you get with these hemicelluloses. I'm just numbering the carbons here. We can get branching at that position, the number 6 carbon. So we can get 1,6 bonds as well as 1,4 bonds. So we can have this sort of motif, maybe a 1,4 mannose, 1,4 glucose. I'm not drawing this out. There is a convention for writing this down, but again, that's one of the things you'll have to look up. So that would say, oh, I've got a 1,4 bond mannose to glucose. But we can also have here a 1,6, which then goes off to another molecule, like another mannose molecule. So there's branching that occurs with these as well. So these structures are rather more complex than cellulose. The linear parts of these can associate and they can still form part of like a dietary fibre in the plant. It's always better to have your dietary fibre in plants rather than dietary supplements. So just eat good food, I think is the message there.